So good morning, good afternoon, good evening, depends where you are in the world. So welcome to everybody for the first talk of the season 2023 of the CASS Talks organized by CASS Chapter Rio Grande do Sul in Brazil. So today, for this first talk of the year, we are happy to have here Professor Luca Carloni from Columbia University in the city of New York. But we are here today to attend the talk by Professor Luca Carloni. So Professor Luca Carloni is a professor and department chair of the computer science at Columbia University in the city of New York, where he leads the system level design group. He holds a laureate degree summa cum laude in electronics engineering from the University of Bologna, Italy, and master engineer from the University of California at Berkeley, and a PhD in electrical engineering and computer science from the University of California at Berkeley. Luca received the Faculty Early Career Development Award from the National Science Foundation in 2006. He was selected as an Alfred Sloan Research Fellow in 2008. He received the ONR Young Investigator Award in 2010 and IEEE CIDA Early Career Award in 2012. Luca is an IEEE Fellow, class of 2017. His research interests include heterogeneous computing, system-on-chip platform, computer design, embedded systems, and open-source hardware. Luca co-authored over 108 referred papers in these areas. The system-level design group has made several research. I'm covering here the contributions available in public domain, including in particular ESP, the open source system-on-chip platform. So thank you very much, Luca, for accepting our invitation. And the floor is with you to start your presentation.
Thank you, Ricardo. Thank you very much for the invitation, for the introduction. Thank you, IEEE CASS and Rio Grande do Sul, for giving me this opportunity today to present ESP, which is an open source platform for heterogeneous computing that is the result of about 10 years of research and teaching at Columbia University. So our research on ESP was and still is motivated by the consideration that information technology has entered the age of heterogeneous computing. And in this context, the system on chip has become the dominant computer architecture. Across a variety of application domains, from embedded devices at the edge of the cloud to data center blades at the core of the cloud, computing systems rely on highly heterogeneous system on chip architectures. And these architectures are heterogeneous because they combine general purpose processor with a variety of specialized hardware accelerators, GPUs, memory hierarchies, and increasingly also reconfigurable engines and analog blocks. The migration towards heterogeneous SoC architecture will accelerate across almost all computing domains, from IoT devices, embedded system, to mobile device, to data center, even to supercomputers. And my prediction is that the set of heterogeneous system on chip in production in any given year in the future will be itself an heterogeneous set, meaning no single SoC architecture will dominate all the markets, which offer a beautiful variety of opportunities for research and for entrepreneurship. Now, heterogeneity is becoming the dominant paradigm because it improves energy efficiency and performance. However, it increases design complexity. And this is an natural characteristic of a heterogeneous system. It makes more difficult the task of design, verification, and programming. Why? Because it's a system that consists in a collection of diverse components is intrinsically more difficult to design, to verify, and to program. At the same time, the difference among heterogeneous components translates into diminished regularity in chip layout and the need to perform different verification tasks. At runtime, the presence of many heterogeneous components complicates the hardware-software interface and the management of shared resources. For example, access to off-chip main memory and use of the tight on-chip power budget. And with it is the case, it has been said by many, that with each system-on-chip generation for a given product, the addition of new capabilities is increasingly limited by engineering effort and the engineering team size. So in this context, we believe that the biggest challenges are and will increasingly be found in the complexity of system integration. In this context, we also believe that open source hardware offers a unique opportunity as a vehicle, a tool to re-energize the innovation in the semiconductor industry, following the model of the proven success of the open source software ecosystem. Now, the momentum of open source hardware has been building in recent years. The number of open source hardware projects continues to grow in academia. Industry participates in various ways, and the support comes from multi-institutional organizations for government programs and a variety of contributions. To date, however, most open source hardware projects have been focused mostly on the development of individual system-on-chip components. Very important, like a processor, a specialized processor like a GPU, a specialized accelerators, a network on chip. And this is certainly useful, but leaves open a challenge that we consider particularly critical and can be summarized with this question. How can we realize a complete SoC for a given target application domain by efficiently reusing and combining a variety of independently developed, heterogeneous, open source hardware components, especially if these components are designed by separate organizations for separate purposes? So, answering this question, we believe, requires enabling design reuse and collaboration to directly mitigate the design complexity challenge. And we think that a promising path goes through innovation of the SoC architecture, as well as the computer-aided design methodology that we use to design this SoC architecture. Indeed, architectures and methodology must be developed together in order to be effective. And this approach is captured by the concept of platform. A platform is precisely the combination of an architecture and a methodology. Now, an SoC architecture enables design reuse when it simplifies the integration of many components that are independently developed. An SoC methodology enables design collaboration when it allows designers to choose the preferred specification languages and design flow for the various components. So it is the effective combination of the architecture and the methodology that makes a platform a tool that allows to maximize the potential of open source hardware. Why? Because it can do so by scaling up the number of components that can be integrated in an SoC and by enhancing the productivity of the designers who develop and use them. And now we come to ESP, our project. ESP is an open source research platform for system-on-chip design. As I said at the beginning, it's the result of over 10 years of research, and it has been an open source project now for 3.5 years. ESP combines a scalable architecture with a flexible computer-aided design methodology. The scalable architecture allows rapid design and FPGA prototyping of complex system-on-chip, and now has been also been proven as very effective to develop prototype of actual chips, research chips, like the one shown in this picture, which is a snapshot of the ESP website taken a few weeks ago, which is on the right side there. So it allows this fast prototyping by combining newly designed components with open source hardware components which are available in public domain, contributed by a variety of organizations, academia, and industry. For example, RISC-V processor or deep learning accelerators. So this is the architecture. The flexible methodology guides the designers of the SoC through the development of new components, in particular through development of specialized hardware accelerators, and through the integration of this component, combined with other open source components, into the heterogeneous SoC architecture. The methodology does so by supporting a variety of specification languages and embracing a mix of open source and commercial CAD tools. So the rest of my talk now is structured along these three essentially main segments. First, I will give an overview of the ESP architecture. Then I will give an overview of the ESP methodology. And then I will give a short overview of how we use ESP, particularly at Columbia University, for research and for teaching. So the ESP platform is effective precisely for this combination of the methodology and the architecture that have been developed together. And so let's start from the architecture. The architecture is style-based. So for a given application domain, the SoC architect decides the structure of the SoC by determining the number and the mix of tiles. So for example, in this picture, you see an instance of a possible SoC architecture which contains 16 tiles organized in a 4x4 matrix. You could have, of course, other combination, like a matrix of 6x4 tiles, for example. A tile may contain a processor, an accelerator, or a memory. There are also another couple of tiles types, but these three are really the main types of tiles. Tiles are typically connected with a multi-plane network on chip, so with multiple network on chip that share some of the elements to control them. The ESP architecture implements a distributed system that is inherently scalable, modular, and heterogeneous. Processors and accelerators are given the same importance in the SoC. This system-centric view, as opposed to a processor-centric view, distinguishes ESP from many other interesting open source hardware projects that we have seen appearing over the years. In ESP, the approach is truly system level. Now let's dive into each type of tile, starting with the processor tile. A processor tile contains a processor that is chosen from at design time from a set of available processors. Right now, the available processors are the one listed here. So we have a RISC-V CVA6, formerly known as Ariane, 64-bit processor, a SPARC V8 Leon 3 32-bit processor, and a RISC-V IBEC 32-bit processor, which is more for, if you will, low power and IoT type of application. If we focus on the first two types of processor, which support different instruction set architectures, RISC-V Ariane and SPARC Leon 3, we can say that both processor cores boot Linux. Both comes with a private level 1 cache, as shown on the right top corner here. And the ESP tile augments them with a unified private level 2 cache of configurable size, again, as shown in the right picture. The processor integration into the ESP SoC distributed system is transparent. What do we mean with that? Is that no ESP-specific software patches are needed to boot the Linux operating systems and run applications on top of the operating system. A MESI directory-based protocol for coherency provides support for system-level coherency on 3 dedicated planes of the network on chip. Typically, in many of the ESP systems that we prototype nowadays, we have 6 network on chip planes. So 3 support communication among the processor and the memory in a coherent way. 1 supports interrupt request, IO request, and also a variety of diagnostics. And then we typically have 2 network on chip that are used for communication among accelerators with the external memory. The second type of tile is the memory tile. Now, in ESP, you can have multiple memory tiles, 1, 2, 4 in typical system that we prototype nowadays. And the number of memory tiles is another aspect of the configurability of ESP. It can be configured at design time. Once you have a certain configuration, all the necessary hardware logic that supports the partitioning of the addressable memory space and that support the coherency is automatically generated. In fact, a memory tile, as shown on the bottom right corner, contains a portion of the last level cache and the corresponding directory, and their size is also configurable. Then you have additional logic that implements the coherency protocol and the mechanism for coherent DMA, which are necessary for the operations of the accelerators. The third main type of tile is the accelerator tile. Each accelerator tile contains the specialized hardware for a loosely coupled accelerator that execute a coarse-grained task. So these accelerators are typically designed independently from the processor. In fact, you can change the processor at design time, even from example from Ariane or Leon 3, and you don't have to change the accelerator, nor the software used to execute the accelerator. You have to recompile, but not more than that. So these are loosely coupled accelerators because they operate independently from the processor at runtime. They execute tasks which are fairly complex, and they do it, of course, in a more efficient way than a corresponding execution in software on the processor could offer. And they do it by exchanging large amount of data with the memory hierarchy. Like any other type of tile, the accelerator is encapsulated into a socket, and this socket acts as an interface and provides certain important services and follows the protocol and shell paradigm of latency-sensitive design. So the socket really plays a critical role both at design time and at runtime. At design time, it decouples the design of the content of the particular tile from the design of the rest of the system, the other tiles, the network on chip, the whole SoC. At runtimes, it provides a set of accelerator-independent platform services, like, for example, the services to support various coherency models that one can change dynamically every time an accelerator is invoked by software for a certain workload, fully coherent, last level cache coherent, non-coherent, as indicated in this slide. Now, let's focus a little bit more on the concept of the socket, which is really important both for the architecture of ESP and for the methodology of ESP. And let's focus that from the perspective of an accelerator. What you see here in this picture is that you have two main classes of accelerators that you can eventually integrate into a system in ESP. On the left-hand side, you have a newly developed accelerator, an accelerator that you can develop with the ESP methodology using some of the various design flows that are supported. On the right, you have a third-party accelerator, which has been already designed and maybe made available in public domains as open source hardware, and that you may want to integrate into ESP. So thanks to the concept of sockets, each particular accelerator can be designed independently from everything else in the system. And the ESP methodology is flexible in the sense that it accommodates accelerator design with different flows, as we said. So let's focus 1 second on the left-hand side on the newly designed accelerators. For instance, they can be designed and optimized and ultimately automatically synthesized starting from a high-level specification, like specification given in C, in synthesizable C, C++, or System C, and using high-level synthesis. Also, as we will see later, we have a design flow for specification given for a certain application domain, particularly the application domain of embedded machine learning. You can also design accelerator using register transfer level approaches, chisels, system Verilog, or Verilog. Now, the ESP methodology guides the design of an accelerator by means of a template that helps define the internal microarchitecture. And a crucial component of the architecture is the interaction between the data path that executes typically the algorithm that is accelerated in hardware with the private local memory, or PLM, as shown in the picture on the left-hand side, which is really important for an effective computation, a computation that has to give better performance and better energy efficiency than what could be obtained by running this particular algorithm in software instead of having a hardware accelerator. The template also defines the processes to transfer data between the private local memory and the main memory, and promotes the pipelining of this communication with the internal computation. Through the ESP services which are implemented by the accelerator socket, the designer can focus on the design of the accelerator without having the burden of reinventing the wheel with respect to implementing, for instance, the mechanism for accelerator configuration, the configuration register that you see at the bottom there, or the mechanism to do DMA, or to handle virtual memory, or the mechanism to interact with processor through interrupt request. The network on chip interacts only through the socket. And we have these multiple planes that play a role also for the accelerator, as shown in the picture. Now, all this that is done when you implement a new accelerator using the ESP methodology, as we will see later, to a large extent applies also for third-party accelerator. You need to take advantage of the ESP platform to instance a socket that encapsulates an accelerator. An example of a third-party accelerator that was integrated and really was the driver to implement this version of the accelerator socket that you see on the right-hand side of the picture is the NVDLA, a complex, configurable open-source accelerator designed by NVIDIA. And when we integrated this design, the NVDLA, we had two very important confirmations. First, that the modularity of the ESP architecture allows to quickly synthesize a simplified socket. In this case, the accelerator came with some of the services that we typically have in the socket. And so we could, thanks to the modularity of the design of the socket, we could just omit the instances of these services. And also we had the confirmation of another, which was very important for our research group, that of the effectiveness of the choice that we had made for the design and integration of the accelerator in ESP. Because this NVDLA is programmed and communicates with memory exactly like all the other ESP accelerator in this loosely coupled fashion. Now, once we have the accelerator integrated in SoC together with the processor, the memory, and the tile, then you have, if you will, a corresponding of this hardware socket that I just described, and this is the software socket, the ESP software socket, if you will. This is relies on the ESP application programming interface, API, which simplifies the invocation of an accelerator from an existing application. So for a given application, the software execution of a computationally intensive kernel that you want to assign to the accelerator can be done by means of a single function call. So for example, here, this figure on the right-hand side shows the case of an application which has 5 computational kernels. 2 are executed in software, while 3 are implemented by invoking corresponding accelerators that have been designed, optimized for these kernels. And so you do this through this simple API. You see here some of these primitives, ESP alloc, ESP run, ESP free. And in particular, the argument of the ESP run function contains a set of configuration parameters that specify which accelerator to invoke and how to invoke them. With a single invocation of the ESP run, one can invoke multiple accelerators so that it can map data flow of computational kernels onto multiple accelerator tiles that communicate on top of the network on chip via point-to-point channels. Data are shared across accelerator and processor without any copy. There is no need to make extra copy. Instead, they are allocated in an efficient way to improve the accelerator access to memory hierarchy without compromising the software performance. ESP, as I said, comes with a rich set of platform services, a set that continues to grow thanks also to contribution of others. These platform services are organized in a modular way, and this is one of the key to the rapid prototyping of a full SoC. At design time, it's possible to choose the combination of services for each tile. At runtime, many of these services offer a reconfigurable option. For example, the coherency mode of each accelerator can be reconfigured dynamically based on the particular workload for each accelerator independently and for each independent invocation of the same accelerator. Dynamic voltage and frequency scaling can be applied at the granularity of each tile. And this fine granularity applies also for such services as performance counters and operation monitors. Data flow graphs can be dynamically set up on the network on chip to connect the accelerator. And consequently, the DMA transactions are routed directly to memory or between accelerators. So these leads us to the second segment of this talk, which is now focused on the ESP methodology. So with an understanding of this ESP accelerator, of the ESP architecture, before we dive into the methodology, it's good to summarize what are the pillars of the ESP approach. So one should be clear, and I already mentioned it, I want to state it again. So we are interested in developing platforms, not just architecture. And again, a platform is the combination of a computer architecture, which in our case is a system-on-chip computer architecture, not just a processor architecture, and a companion design methodology. And we believe that in developing SoC architecture, it's critically important to move from processor-centric to an SoC-centric perspective. The processor remains super important, of course, but is one component among many other important components. So we also think that it's very important to think at the system level, and we recommend to raise the level of abstraction in the design process wherever is possible. In particular, we try to move from RTL design to domain-specific system-level design with the help of high-level synthesis for the design of accelerators. But we keep supporting different abstraction level and design flows, so it's still possible to design an accelerator in RTL, or many key components of the SoC infrastructure, like the network on chip, are designed used at the RTL level. And then, of course, what we're trying to do with ESP, and this is always we keep in mind, is to promote open source hardware by build libraries of reusable components and support the integration of third-party intellectual property component developed and made available by other researchers. So with this principle, the ESP vision, which is a little ambitious, but it's important to have ambitious visions, is to allow application domain expert one day to design their own SoCs. As of today, what we have is that the ESP methodology supports multiple design flows. This allows the creation of a rich set of heterogeneous components, a rich library of components, start for different abstraction levels, as we said. So, of course, you can design component with the traditional RTL design flow. We advocate the use, however, of flows based on high-level synthesis, and we support various commercial high-level synthesis tools, particularly for the design of accelerators, which are often the part of the SoC which differentiates the SoC, the part where there is the added value, the reason why you build an SoC for a certain application domain. And in this context, we keep investigating how to further raise the level of abstraction. And for example, by leveraging a project, another open source project to which we contribute, but we don't lead, which is called HLS for ML, we have, in recent years, integrated a design flow that allows for embedded machine learning, allows to take description of neural networks using some of these very common frameworks like Keras and PyTorch, and with the help of HLS for ML, obtain a synthesizable specification that with a high-level synthesis tool leads to an accelerator that then we have integrated into with a design flow inside ESP. So all these approaches lead to the creation of a library of hardware intellectual property blocks and components that continue to grow in its size and its variety. And there is a corresponding library of software components, including Linux application, bare metal application, device driver, and third-party accelerator software. And then we have a graphical user interface, which supports the SoC designing team to build a particular instance of an SoC ESP architecture, like in this case, a 3x3 tile matrix in this little example. And then through this integration, there is also support to have often mostly automatic, of course, not fully automatic, sometimes semi-automatic generation of prototypes on FPGAs and prototypes of chips. So these are two possible paths to the implementation of an SoC designed with the ESP platform. So now, I said that the ESP methodology is flexible because it accommodates this different design flow and different CAD tools. These flows are not fully automated, but they are largely automated. And so this picture tries to capture this idea. And it does so by using the color coding you see defined on the top right corner there, which shows the different degree automation of the most important steps in the design of a new accelerator. As I said, an accelerator often is the main component, together with the other accelerator, that differentiates an SoC. And so a lot of our effort is in support the design of accelerator while avoiding to reinvent the wheel for the architecture that is around the accelerator. And so for machine learning inference application, I said that we have this support for the machine learning, embedded machine learning domain. So ESP integrates the open source HLS4ML package, which allows even the application-specific portion of the accelerator to be automatically generated from models given in Keras TensorFlow, for example, or in PyTorch. For generic application, the templates generators as a script that creates a fully working skeleton. Is the skeleton of the accelerator with, for example, user-defined registers. And this simplifies quite a bit the manual effort of the design. The script also generates device drivers, a unit test bench, a user space application. So it enables simulation, full system simulation, and full system prototyping really out of the box. We also have a flow for the integration, and this is largely automated with some aspect of interactivity, all the way leading to a prototype on FPGA. And even when the goal, as I'll describe later, we have made quite a bit of progress of the goal of building actual chips, even in that case, we typically first do an implementation which emulates the chips on FPGA as much as possible. Now, thanks to the ESP services, which are provided by the socket that I described when I was describing the architecture, the hardware socket as well as the software socket, application developer and hardware engineers can really focus more on the high-level specification of an accelerator. And do this in a way which is decoupled from the issues of, for example, memory access, system communication, hardware-software interface, interrupt, and so forth. So they can start from the accelerator skeleton that I just mentioned, and developers can explore the space of the alternative design implementation. And if you do this, typically from accelerator, starting from a high-level specification language, like C, System C, and using high-level synthesis, and you navigate this space at the so-called programmer's view, because it's closer to a certain extent to software, although you're designing really hardware using high-level synthesis. And you can, by working at this high level of abstraction, you can explore a much broader, rich set of alternative implementation. And you can take advantage, of course, of all the high-level code transformation and high-level synthesis knobs that are made available by modern high-level synthesis tools. So for every particular specification that you can give of an accelerator, like you see here on the top plane, version 1, version 2, version 3, each of them is a specification, for example, in System C or in C++, which is synthesizable, you can obtain many different implementation at the RTL level. And of course, then this doesn't remove completely, actually, it enhances the design effort. And so you can create, then make modification in the direction of moving in the design space, maybe by trying to improve area on power dissipation or improve performance. And of course, this is typically a trade-off in hardware design, and you have trying to obtain Pareto curves where you have Pareto optimal implementation in this bi-objective optimization space. So typically for an accelerator, you end up having many alternative implementation in the library. And it is crucial to understand that each one of these implementation can be chosen and integrated into ESP in the tile. So you can change for a particular accelerator which implementation you use in the tile without having to change anything else in the ESP system. The socket embraces the particular implementation, interfaces in the rest of the system, and allows you to change it at design time based on your particular need to be in one particular point on the trade-off curve between performance and area power dissipation. So this is really thanks to this concept of socket, which is inherited for the concept of the protocol and shell paradigm of latency-sensitive design, which is the foundation for supporting this design time seamless choice of different RTL implementation. What do I mean with that? You have that inside the socket, you can replace any one of the implementation that you have trained to high-level synthesis, and the differences in latency, the differences in clock frequency respect to other parts of the SoC, are absorbed by the interface, by the socket that acts as a shell and interfaces this with the network on chip and provide the services. So this is the root of that important concept, which is the coupling through the socket. Now, once this is clear, this is a picture shows the graphical user interface of ESP, the first generation of the graphical user interface, which allows, as I said, to quickly put together the architecture on SoC given the components available in the library. So once you have developed your accelerator, you created your library, and you can now choose from the newly developed accelerator and the other accelerator. Then through this graphical user interface, you are guided to a set of choices. So for instance, you can choose the size of the tile matrix. In this picture, eventually is a 3x3. And now the animation will loop. So we start with a 2x2, and you see that, for instance, you can change the configuration and say, okay, I want actually a 3x3 architecture for the tile matrix. And then you can choose the mix of components in the tiles. And you can select for each particular tile, particularly if it's an accelerator, which implementation that I mentioned you want out of what is typically a collection of alternative implementation which are Pareto optimal. Some offer better performance in exchange of higher cost of area and power. Some offer less performance, but they provide gains in terms of power and area. You can select the desired processor cores among the ones that are available, the cache hierarchy configuration, the clock domains for each tile. You can enable monitors, system monitor, that allows you to evaluate, for instance, on FPGA, your design. And then, of course, you can repeat this fairly efficiently. And this allows you to have rapid prototyping and make architectural decision and focus on that. So after the microarchitectural decision at the level of the accelerator, the architectural decision at the level of SoC. Okay, this year, we actually reached a very major milestone with ESP, together with collaborators in industry, at IBM, and in academia, particularly at Harvard University. Together, we designed, fabricated, and tested successfully, and published the first chip designed with ESP. This is called the Epoch Zero chip. It's part of the Epoch project, which is a collaborative project with these other institutions I mentioned. So what you see here is what was published in a paper last September, is the first chip completely designed with the ESP platform. Before that, most of our demonstrations were based on FPGA prototyping. And so, as you can see, is a 4x4 tile architecture, shown on the left-hand side. It contains a mix of accelerator designed by our team, like FFT, accelerator for FFT or for the Viterbi algorithm, and accelerator available for public domain. They already mentioned NVDLA accelerator. It contains a RISC-V processor, which is been designed and made available in public domain by ETH Zurich, and for last level cache memory tiles and I/O tile. Has been implemented in 12 nanometer FinFET technology, and it successfully boots Linux and runs applications that can take advantage of the accelerator. So this has been a very major milestone for us because it proves, if you will, the success of our approach in design actual chips. In fact, this chip is the first of a series of chips that we designed. And after that, we have already designed a second chip, which is called the Epoch 1 chip, which has, compared to the Epoch 0 chips, more accelerator, more tiles, more clock domains, more power domains, more area. So it's a more complex chip. And this chip, which is has been fabricated, is under testing currently, also boots Linux and runs a more complex application thanks to the accelerator. So the data that you, as you can see, is a 6x6 tiles matrix. So this, and the area is bigger. You have sophisticated power management, frequency and power management with 37 clock domains and 23 power domains. But besides the architecture, one important aspect of the methodology is if we compare the effort of the design team for the Epoch chips, which was designed in 4 months, and the Epoch 1 chip that was designed in about 3 months, even though it's a more complex, a little bit more than 3 months, even more is a more complex chip, and was designed more or less by the same team of 6 to 7 engineers during this period of 3 months. And so this, in our view, is an important demonstration also of the scalability, not just of the architecture, but also of the methodology in the design of this complex chip. Of course, this is made possible by taking advantage of the open source hardware community, which has made some of the components available, and we integrated using the architecture and the methodology that I described. Besides this, I'm going to now shift to the third and last segment of my talk by just giving you a series of snapshots of how we have used ESP in the past to do research or to do other type of prototyping. I show you right now these chips. Before that, the emphasis of ESP was in designing implementation of FPGA. One of the most complex was done a few years ago when we completed this, and is shown here of the graphical user interface of the time, this of ESP, this architecture, this SoC architecture implemented on FPGA of a 4x4 tile SoC, where you have one processor, which is the pink tile in the picture on the left hand, on the top left corner, and then you have 12 accelerators in golden, if you will, and 2 memory tiles and 1 I/O tile. So this, at the time, this is already a few years old, this work. All the accelerators are supported by 5-plane 2D mesh NOC. And what you see in the middle is the live diagnostic of what, with our graphical user interface, of the operation of this SoC, which is executing application for wide area motion imagery, so a form of computer vision, the front-end pipeline of this WAMI application. And what you see also is live here, the traffic on the network on chip. And one thing very interesting that we did when we used this application to drive the development of ESP is that we demonstrated, for instance, how quickly one can change the architecture in ESP by, for instance, adding one more memory tile. As it's shown here, there are 2 memory tiles, but in the first version, and we could then compare the two, we only had 1 memory tile. By adding 2 memory tiles, automatically we could split the memory addressable space. We could distribute the traffic. Instead of having just one hot spot to communicate with external memory, we could split it in 2 spots, a little less hot, and therefore reducing congestion on the network on chip, and ultimately achieve better performance in executing this particular application. So this is an example of what you can do with ESP in terms of FPGA prototyping. Another thing that we demonstrated a bit later was how ESP provides fairly good scalability. In this case here, you can, and also this shows how you can use the graphical user interface but when you are in a scenario where you want to reason about maybe duplicating a certain particular accelerator. So in this case, we start from the bottom right corner where we have a simple 2x2 system with 1 processor, 1 I/O tile, 1 memory tile, and 1 NVDA accelerator. And then we move up by doubling the number of accelerator and then doubling it again. And as we do that, also doubling the memory tiles. And as I told you, when we double memory tiles, we add more memory tiles, automatically the last level cache and the directory for supporting coherences are partitioned so that the designer doesn't have to be concerned about that. And what is possible to obtain in this case is that we double the computational performance for certain applications which have a good level of parallelism tile-wise. In this case, is a form of inference or a neural network executing on the NVDLA, as long as we can support this additional computational performance with good communication performance with external memory. So this is what you obtain, this improvement in frame per second normalized, which looks like linear, precisely because you double the accelerator, double the communication channels. But this is just as an example, a simple example, if you will, of how once you have all the components and now you start moving from the design space exploration at the accelerator level to the design space exploration at the architectural level, how basically ESP can assist you to do that. Another thing that I mentioned before, I'm going to do a little bit quicker here, is that we have integrated for the AGLS for ML, this other open source project that which we participate, we have integrated with ESP in the sense that it's possible to use AGLS for ML, which allows you to compile this description of neural network mostly for inference, although it can be used also for training, into synthesizable specification of accelerator. And now, once you have this accelerator, the accelerator can be integrated into the ESP architecture with the concept of socket that I described. And this is described in the paper that you see at the bottom. And this is just, for those of you who are maybe not familiar with JSLS4ML, is an invitation to take a look at this open source tool, which has been developed by a wonderful community of people working on research in physics. And then one last example is how ESP can be used to do also research from the viewpoint of computer architecture research. So this is a paper that we published a couple of years ago at Micro. It's called Chameleon, and is about orchestrating accelerator coherence in heterogeneous SoC, and do so by using reinforcement learning. So the particular idea here is, as I may have mentioned, is that each accelerator in ESP can be integrated in a socket which can support different coherency model. For example, fully coherent, which means that there is full coherence between the accelerator, private local memory, and the cache of the processor. Or you can have last level cache coherence, which is coherency between the private local memory of the accelerator and the last level cache, but not the processor. Or you can have coherent DMA, where again, passing through the last level cache partition, or you can have not coherent DMA, which still works because the application that invokes the accelerator is suspended until the accelerator, the thread that invokes the accelerator is suspended until the accelerator has completed its operation. Now, what we demonstrate, what we show in our papers is that most of the time, the choice is for accelerator is between non-coherence and last level cache coherence or coherent DMA. Fully coherent is often doesn't provide such a big advantage. But in any case, it's possible in the socket to make it a decision, not at design time, at runtime. It costs a little bit of error in the socket, and then every time one particular accelerator is invoked by the application, the particular coherency mode can be selected. If one does that, then the question, however, becomes, if I start having many accelerators on a network on chip, on a large SoC, and multiple workloads happening at the same time, what is the best choice? And so this paper provides an approach where it shows that with reinforcement learning, you can change this choice in an optimal way. And what I guess, besides the particular contribution of the research of the paper, what I guess this paper shows is that it's possible to use ESP and FPGA prototyping in particular to investigate certain research problems, which really it would be very difficult to investigate only with simulation, because in order to, for example, to see this pattern and the difference in using different coherency modes, you need to run very large workloads with huge amount of data on top of the operating system. And this would be very time-consuming if done in simulation, while it's very feasible if it's done using FPGAs. Finally, I want to say that going back to the ESP website, there are quite a bit of resources that we try to contribute, including resources to support teaching. We have been using ESP at Columbia now for about 10 years to teach a course called System on Chip Platform, which is a course where students, both senior students at the undergraduate level and master students and some PhD students, learn how to master certain aspects of hardware and software of integration of heterogeneous component into complex systems like an SoC, design new components that are reusable. So the goal is not just to design one version of the component by using high-level synthesis, a set of Pareto optimal implementation of a component such that this increases usability because it provides alternatives. In one particular SoC, you can use one implementation, which is higher performance. In another one, you may want to use a different implementation of the same accelerator that provides better saving in terms of area and power. And how to evaluate, not just at the accelerator level, but at the system level, design in a multi-objective optimization space. Another thing that we are doing parallel, this happened last year, and is very much related to our efforts in research, is that we are trying to build this community of people who are interested in doing computer architecture research and computer-aided design research by leveraging open source. So we did the first OSCAR workshop we organized last year in New York City, and we are in the process to organize a second OSCAR workshop this year. So stay tuned for that. And so this brings me to my final slide, where, so in summary, I say that we contribute ESP to the open source hardware community in order to support the realization of more scalable architecture for SoC that integrate more heterogeneous components thanks to a more flexible design methodology, which accommodates different specification languages and design flows. ESP was conceived as a heterogeneous integration platform from the start and has been tested through years of teaching at Columbia University. So we invite you to take a look at ESP, use it for your projects, and contribute to ESP, if you will. And with this, besides telling you that you can find many of the papers that I mentioned throughout the talk in our website, I thank you very much for your attention and for this opportunity.
Well, thank you very much, Luca, for this very nice, interesting talk. So now we are open for questions. So who has any question, please write the question in the YouTube channel ASAP. So we have one question from Purma Carmacar from University of Sevilla, Spain. So which interface is used in ESP socket in between read and write and configure and done, like in third-party socket Axie4 and the APB is used?
This is an excellent question and is very much at the core of the interfacing components. At this time, depends on the flow. For the third-party flow, is very much based indeed on Axie and APB, Axie for the data part and APB for the configuration. If you develop an accelerator with one of our internal flows, there is an interface which is more like our interface. I don't want to say proprietary because open source, but our own interface. And we are thinking, as we are going to have a new release soon, and then in future release, to consolidate these, and we are thinking about using more standard interfaces for all types of accelerator. But certainly when you integrate third-party accelerator like NVDLA, that's what the interface you have.
Okay, thank you. So I see no more questions here in the YouTube for the moment. So I have one.
Please.
Do you have a list of the hardware accelerators that you have available in the?
Yeah, there is a list available on the website. On top of my mind, I can remember that there are often accelerator for signal processing that we develop. So accelerator like FFT of 1D, 2D configurable, separate accelerator optimized for that. We have accelerator, I mentioned WAMI, so some of those accelerators are available, some accelerator for computer vision. We have accelerator for related to, if you will, linear algebra, fairly sophisticated ones that we have released. And there is, and then there are the accelerators we did not develop, and we are trying to integrate. One we did, which is the NVDLA small, made available. And so there is certain opportunity to continue to grow that set. And this is actually what one thing I was not able to mention, but if you visited the ESP website, you see it, is that the documentation of ESP to a large extent is based on these hands-on tutorials. And the hands-on tutorials are a series of smaller tutorials that focus on particular aspects. So for instance, how you bring up the system, how you design an SoC with one single core, how you design a single SoC with multiple cores. And there are, of course, a set of tutorials focused on accelerators. And so it's possible to, if a researcher or a student is interested in developing an accelerator with one particular tool, to follow that tutorial and ultimately contribute to the accelerator. And we will be happy to integrate it in the library.
Yeah, one question, how difficult is to integrate a new hardware accelerator or new processors in the library?
It depends. It depends on the hardware accelerator and the processor. So if you have an hardware accelerator third party already designed, and that it has a characteristic similar, for instance, to the NVDLA, which has been our driver for the third-party accelerator, then one can follow that process. And I would say, sure, it is relatively easy in the sense that you can follow those steps and take advantage of the interfaces that we have already built. Similarly, for if you want to develop a new accelerator and you decide to use one of our flows, then the integration is very seamless. With respect to processor, the situation is a little different. Every time you integrate a processor plays a certain important role. So again, now we have three, I said, but let's focus first on the two more high performance, if you will, although they are still processor high-performance embedded application available in public domain. So they speak different ISAs, RISC-V as Spark, and they have different endianness. So those probably been resolved. And in particular for the Ariane processor from Zurich, RISC-V, we have integrated, and with the level 2 cache, we follow the standard of the AXI standard. So I would say that if one, for instance, is interested in integrating a new processor like that for RISC-V, for that, they can follow those paths. It probably a little bit more complex than an accelerator, but still doable. If one comes with an architecture of the processor which is very different, then in some sense the software, the level 2 cache would have to be adapted, would have to be probably designed. It's doable, we have done it, and it can be done in a way that is very modular so that the network on chip and the last level cache and so forth don't have to be redesigned.
Okay, thank you. I have a question by Professor Altamiro Suzin. Thanks for a nice talk. I was wondering what main guidelines to design for testability in a so complex system with different course designers.
That is a very good question. There is certainly room, I'm very frank, room for improvement in terms of in terms of the verification aspect and the testing aspect. Now, we successfully, as I said, designed many FPGA prototypes and now 2 chips. So I would say 2 things. While there is room for improvement, I think the structure of ESP, particularly the choices that have been made at the architecture level, really gives some certain of a path in design for testability. I'm not an expert in design for testability, but I know that the coupling design concern is an important principle. And this is something that in system level design we do quite a bit. And so in ESP, for instance, the network on chip can be tested, has been tested and validated independent from the accelerator. And let's say a new team wants to design a new network on chip, it would be possible to do it independent from the design of the accelerator. Individual accelerators can be tested and designed independently. And once you have the chip back and you test the chip, the fact that you have this tile-based structure allows you to really focus also on testing particular components before you zoom out and test the whole system. So I would say that the architecture, the tile-based architecture helps. There are principles of verification, assume guarantee, and decomposing the design that are naturally supported, but there is certainly room for improvement in refining even more the methodology for verification and for testing.
Okay, thank you very much. I don't see more questions here. Only a question by Apurma, if it would be possible to get a copy of the slides. Anyway,
I think many of these slides, maybe there are a few new slides on this talk, particularly related to the chip, but yes, eventually we will make them available as we have done for other talks on the website. So if you visit, I would invite you to visit already the ESP website under talks and under tutorials, and you find quite a bit of slides, including many that the ones I presented today, and then most likely we will put eventually also the slide for this talk, which has a few new, not too many news.
Okay, anyway, the talk will stay available in the YouTube channel. So anyone that wants to see again the talk, anytime it's possible. So, so thank you very much, Luca, for your very nice work, very nice project, and very nice talk. And I hope to see you in person in the near future.
Thank you, Ricardo. Thank you for the invitation, and thank you to CASS and Rio Grande do Sul for organizing this. It has been a wonderful opportunity. Thank you for the opportunity.
Thank you.